let's now talk about critical numbers, or places where critical things happen. Let a function be defined at C. If f prime of C equals 0, or if f is not differentiable at C, then C is a critical number of f. So notice the C is in the place where x would be. C, a critical number, that is an x value. Critical numbers are x values. Remember I said earlier, critical numbers where something critical is happening. We like to think of it like that, where something critical happens. So what does that mean, critical? Well, like a drastic change in slope. For example, if we go back to those first pictures, a drastic change in slope could be where the slope changes from negative to positive or positive to negative. Something critical is happening there. So what's the slope where something critical is happening? Well, here at this relative min, the slope is 0. Well, remember our word for slope is derivative. So the derivative is 0. In fact, at this critical point where something critical is happening, like the slope changes from positive to negative, the slope again is 0, or the derivative is 0. What about at this relative max where something critical happened, like the slope drastically changed from positive to negative? Well, the slope isn't 0 here. At this point, the slope or the derivative does not exist. So that's what we're looking for when we try to decide the critical number, where the derivative is 0 or where the derivative does not exist. So f prime is either 0 or doesn't exist, and that's where we identify where we have critical numbers. And remember, those critical numbers are the x values. So let's practice finding the critical numbers of the function. So we just have to figure out where is the derivative either 0 or where is the derivative not exist. So as soon as I see critical numbers, I tell myself I'm looking for where f prime equals 0 or does not exist. So what do I need to find first? F prime. So if I'm going to find f prime and I have a quotient, let's first think, do I need the quotient rule? I certainly don't. So let's just rewrite this function so that I don't need the quotient rule. 9x squared over x cubed minus 27 over x cubed simplifies into 9x to the negative 1 minus 27x to the negative 3. So I've got a more simple function, and now I can say f prime of x, and I can do my power rule. Negative 1 times 9, negative 9. Subtract 1 from the exponent, negative 2. Minus, but negative 3 times negative 27 makes positive 81. Subtract 1 from the exponent, negative 4. Now I rewrite it. Negative 9 over x squared plus 81 over x to the 4th, and usually it's easier if I get a common denominator. So I'm going to say times x squared, so my derivative is negative 9x squared plus 81 over x to the 4th. Now remember our goal, find out where the derivative equals 0 or doesn't exist. And I need to find out where. So remember, ultimately I want the x values. Let's start by saying we have a derivative. Where does it equal 0? So now I take my derivative and set it equal to 0. So what does that look like? Negative 9x squared plus 81 over x to the 4th equals 0. So where does the quotient equal 0 is where the numerator equals 0 if I multiply by x to the 4th. So negative 9x squared plus 81 equals 0, and I can do some dividing and find that x equals 3 or negative 3. Now I want to figure out where f prime does not exist, and if I have a quotient, that's where the denominator equals 0. So x to the 4th equals 0, and that's where x equals 0. But remember, an important part of the critical numbers is f has to be defined at C. Is f defined at x equals 0? Well, look at the original function. If x equals 0, the denominator will be 0. So x can't equal 0. 0 is not in the domain. So x equals 0 is not a critical number because x equals 0 Well, let's write it this way. F of 0 does not exist. But f of 3 exists and f of negative 3 exists. So here are our two critical numbers. Let's take a peek at another one. We know what this looks like. If we were to sketch a graph of this, we know it's V-shaped with its vertex at 0, at x equals 0 is the vertex. So we know where the critical number is going to be. We know the critical number is at 0, but how do we use our calculus to show that? Let's split this up into the piecewise function positive x and negative x when x is greater than 0, when x is less than 0. Well, we usually put an equals with one of these. However, if we have to take a derivative, we're not taking the derivative at a point, just at places on an interval. So at x equals 0, the point would be 0, 0, 0, if we were to imagine it graphically. Now we can take the derivative of each of those pieces. The derivative of x is 1. The derivative of negative x is negative 1. And the derivative of just a point cannot be done. So at x equals 0, the derivative doesn't exist. So using our calculus, we can say the critical number is x equals 0 because that's where f prime does not exist. So there's our critical number because that's where the derivative doesn't exist. Notice this from an AP exam, and it's calculator based. So take your calculator. Let's read the directions. For f prime of x equals this function, how many critical values does f have on the interval from 0 to 10? Notice it doesn't say find them. It doesn't say what are they. How many critical values? So remember what we're supposed to determine. Critical values, critical numbers, is where the derivative equals 0 or doesn't exist. They gave us a derivative. We don't find a derivative. Why is this calculator based? Because we can plug in our derivative into the y equals in a graph. So using your calculator, we're going to go to y equals, and we are going to look at a graph. We are going to observe the graph of the function they gave us, f prime of x. Observe the graph of it. Then we'll be able to see where it equals 0 or doesn't exist. Keep in mind the interval that we're focused on. So I'm going to get my calculator, and I'm going to go to y equals, and I'm going to plug in cosine squared x. How do I do that? Parentheses. Cosine x, close parentheses for the x, close parentheses for the cosine, square it, divided by x minus, I probably want parentheses around that fraction, 1/5. So you can see cosine x, function squared over x minus 1/5. So there's my function. Now I'm going to go, say enter, look at my graph, but let's go to a window and make sure that we're only looking at the interval 0 to 10. So the x min, 0. The x max, 10. That's good. Count by ones. The y min and max, I only care about what's happening around the x-axis. So I don't really care about how big or small it is, but I should make it a little bit smaller so I can see the graph a little bit better. So maybe -5 to 5. We'll see what it looks like. Let's go press graph, and I see there's one place where it's 0, there's another place where it's 0. It's kind of hard to see if there are other places. So I'm going to go back to my window, and I'm going to change it so that I'm counting from only -1 to 1 on the y-axis. We'll spread it out on the y-axis, and we'll graph it again. So here's what I see. I'm looking for where this graph, this is the derivative, equals 0 or doesn't exist. Remember, we're looking for where the derivative equals 0 doesn't exist. Well, it's existing everywhere. Nice, smooth, curvy, no holes, no asymptotes. But I see it crosses once, twice, 3, and that's it. It looks like it crosses just 3 times. So if I'm looking for where the derivative equals 0 on my graph, which we'll do a little rough sketch of. So it came down and went up and down and up and down and up, but it only hit 3 times. So let's try to recreate what that looked like. Down and up and down and up and down and up, but it only hit 3 times. Where did the derivative equal 0? 1, 2, 3, no more. Now it only asks how many, not where, so I'm not really concerned where those are happening, just how many times those were happening. So how many critical values? 3 critical values. That's it.